Hi students, let's get started with our cardiovascular system and our special discussion on the blood. So what is the blood? Well, we use our blood to transport many things throughout our body. We are to transport oxygen, nutrients, waste, carbon dioxide, and hormones. Generally speaking, we move stuff from point A to point B in our body with our blood. And this list of things that are transported can be very, very long. We also use our blood to defend our bodies. We defend against invasions by pathogens. These pathogens most often are going to be in the form of a bacteria or a virus, but can occasionally be in the form of a multicellular worm or helminth, or it can be some other protozoal-based or amoeboid-based infection. We also are going to use our blood to regulate our body. We will move heat from one region of our body to another region. We're going to maintain various salt and water concentrations in the different fluid compartments of our bodies using our blood. And then finally, we can help regulate our body's pH using the buffering systems, the bicarbonate and the phosphate buffering systems of our bloodstream. Within our blood, we find that there is a combination of cells and extracellular matrix. Now, the extracellular matrix of the blood is a unique extracellular matrix in that it is a fluid at room temperature. Recall, the extracellular matrix is the non-living component of a tissue. And this non-living component of the blood is very, very fluid. It has lots of ground substance, but not lots of corresponding fibers in it. So blood overall is a fluid tissue at room temperature because it's lacking fibers in its extracellular matrix. The cells, or the formed elements of the blood, are all going to be made in the red bone marrow. They include red blood cells, white blood cells, and our platelets, or if we use the technical terms, erythrocytes, leukocytes, and thrombocytes. If we look at our blood plasma is overwhelmingly water, 91% water, so it's going to be very liquidy. It's going to have a very serous composition to it, so to speak. It's not viscous. It has low viscosity. Our blood plasma does have dissolved salts in it, ions, and when we say dissolved salts, I don't just mean table salt, sodium chloride. I also mean potassium salts, calcium salts, carbonate salts. There are many different ions, so to speak. So when I use salt in this term, I mean any kind of positive or negatively charged ion is dissolved in the blood, in addition to some larger organic macromolecules as well. Our blood plasma has plasma proteins in it. These proteins that are suspended within our blood plasma, generally speaking, are very abundant. They're very common in our blood and serve many different purposes. Some of these proteins are going to include our albumins. You can think of the albumin as an osmotic or an osmosis regulator. Remember back when we had our chemistry crash course chapter, osmosis is the movement of water across the semi-permeable membrane from an area of high concentration to an area of low concentration. Wow, that's kind of a wordy definition. What do I mean by osmosis? I mean that osmosis is a movement of water from an area where there's lots of water to an area where there's a low concentration of water. And to help change the concentrations of water, we have albumins in our bloodstream that make it so that water is going to there'll always be a little bit of a pulling force to help pull the water back into our bloodstream via osmotic pressure. We also have globulins. We use globular proteins in our blood to transport materials throughout our bloodstream. We have globulins that transport iron atoms, and we also have globulins designed specifically to transport oxygen atoms. Those are known as hemoglobin, and we'll talk about them in a bit. We also have some fibrinogen in our blood. Fibrinogen is a clotting protein. When activated, it turns into fibrin and then forms blood clots. Fibrinogen is the deactivated version. Thankfully, we know we don't want that fibrinogen to massively clot all over the place. As we look at our formed elements in our blood cells, they can consist of our red blood cells, aka erythrocytes, and there's 5 primary kinds of leukocytes, or white blood cells, that we're going to focus on in this chapter: the lymphocyte, monocyte, neutrophil, eosinophil, and basophil. And we'll talk about each of those in more detail later. And then finally, we also have the platelets. Platelets are the cell fragments of these megakaryoplasts. So, class, concept check. Which is the most common formed element? Is it the red blood cells, white blood cells, platelet, or all exist in equal proportion? I didn't actually specify the answer to this question. I didn't spell it out very clearly in the PowerPoint, but if you think about what color our blood is, that'll be a big clue for you. So think about the different kinds of cells in our blood and what the overall color of our blood is. So pause the video and get me an answer. 5, 4, 3, 2, one. The correct answer is red blood cells. A. Red blood cells are by far the most common formed element in our bloodstream. That's why our blood is bright red or dark red. If white blood cells were the most common, we'd have a whitish color. If platelets were the most common, well, our blood would be clotted. And if we had red blood cells and white blood cells in equal proportions, though our blood would be pink in color. Let's continue on. Let's look at our red blood cells and highlight our red blood cells. Our red blood cells are unique in that they do not have a nuclei and very few organelles. And if we think of the nucleus, think back to that nucleus. The nucleus is the organelle that stores most of the genetic information in the cell. So our red blood cells are rather unique in that they don't have the nuclear genome. They are missing our genome. So we think of giving a blood donation to have somebody's genetics calculated or determined. The DNA in that blood donation is not going to be in the red blood cells. When you or from a forensics perspective, that DNA is going to be in the white blood cells that are in the blood sample. Our red blood cells have a biconcave shape. That biconcave shape is kind of a nice way of saying that there's two indentations in our red blood cells, and that increases the surface area of the red blood cell compared to its volume. So we increase the surface area to volume ratio, which maximizes the rate of oxygen diffusion into and out of the red blood cells. Each of our individual red blood cells is going to contain approximately 300 million-ish hemoglobin molecules, and this is a typo here. Each hemoglobin is capable of binding to 4 molecules of oxygen, of O2. So each red blood cell is capable of binding approximately 1.2 billion oxygen molecules. Here we can see the dimple, that's the concave shape. Each red blood cell has 2 dimples, one on each side, so they are biconcave. Within our red blood cells, you will find many, many hemoglobin molecules, approximately 280 million hemoglobin molecules per red blood cells. Each hemoglobin is made of 4 protein subunits. Each subunit within hemoglobin has a heme group, and each heme group is capable of binding to 1 oxygen. And these red blood cells will move single file through blood capillaries to transport their nutrients. So most oxygen in the bloodstream is transported on the hemes of the in the hemoglobin inside of the red blood cells. If we look at carbon dioxide, the vast majority of carbon dioxide, 68%, so we'll just round to 70%, we'll say approximately 70% of carbon dioxide in the bloodstream is actually transported as a bicarbonate ion. That carbon dioxide will bind with water, turn into carbonic acid, and then dissociate into the bicarbonate ion. Why is this a good thing? This is a good thing because if most of the carbon dioxide was transported as CO2 gas in our bloodstream, our blood would be carbonated then. We'd have bubbly blood, and those bubbles would kill us off very quickly. So to minimize the amount of bubble formation in our bloodstream, we take that carbon dioxide and transform it into a bicarbonate ion using enzymes that we have within our red blood cells. To make our red blood cells and any other cell type, we will use our red bone marrow. Something that is unique about the red blood cells in particular, though, is that our red blood cells have a lifespan of approximately 120 days, or 1/3 of a year. So we will actually replace all the blood in our body, all of the red blood cells in our body, approximately 3 times a year, which is, hey, that's kind of cool. It's good to know that we can regenerate our blood that quickly. The hormone that stimulates the production of red blood cells is called erythropoietin, EPO. Whenever the kidney cells sense low blood oxygen, those kidney cells are going to secrete EPO. EPO will then travel through the bloodstream to the red bone marrow of the spongy bone tissue, and when it reaches that red bone marrow, it will stimulate the production of more red blood cells, and that's known as erythropoiesis or erythrogenesis. So erythropoietin stimulates erythropoiesis. And as we have more and more red blood cells made, that causes the amount of oxygen in the blood to go up and fix the problem of low blood oxygen. As red blood cells break down, because they do break down, they will be processed by both the liver and the spleen, where we can recycle macromolecules, vitamins, and minerals from the defective red blood cells. Here's a figure showing the blood oxygen process I just talked about. Whenever we have low blood oxygen, that low blood oxygen will be sensed by the kidney. The kidney will release EPO. EPO stimulates the red bone marrow to make more red blood cells, and then the oxygen carrying capabilities of the blood go up, and the O2 levels go back to normal. If we look at blood doping is any method we have that increases the number of red blood cells in the blood for the purposes of increasing athletic performance. Generally speaking, blood doping is going to cause for a more efficient delivery of oxygen and will make it so we have less fatigue in our skeletal muscle tissues. If a person or athlete is blood doping with EPO, that EPO can be injected into the person several months prior to the athletic event, causing their blood concentrations to go up. However, this is not necessarily a good thing for us. If we artificially increase the concentration of red blood cells in our bodies, we artificially increase the viscosity of our blood, and that thickening of the blood makes the heart work really hard and increases the risk of heart attack and spontaneous clotting elsewhere in our bodies. There are some disorders that have been associated with red blood cells. These are known as anemia, sickle cell anemia, and hemolytic disease of the newborn. Anemia is a general condition that refers to too few red blood cells or low blood hemoglobin counts. And if somebody doesn't have enough red blood cells in their blood, they can't carry enough oxygen, and generally speaking, they feel fatigued. They have a run-down feeling, so to speak. If we look at sickle cell anemia, that's a specific kind of anemia that's caused by a genetic disease that causes our red blood cells to become pointy on two ends. They become sickle cell shaped. And then those pointy, defective red blood cells are very prone to rupturing. And individuals that have sickle cell anemia oftentimes will have enlarged spleens and enlarged livers as they're processing an excess amount of defective red blood cells. And then finally, we have hemolytic disease of the newborn. We're going to talk about that in more detail in our next lecture recording. Hemolytic disease of the newborn is a condition that results when mom's immune system attacks the blood cells inside of baby before baby is born, causing baby's blood cells to rupture while baby is in mom's utero. So that's a big problem. And those antibodies, or those components of mom's immune system, can even stay in baby's bloodstream and continue attacking the baby's blood cells even after baby has been born. So, class, concept check. The most carbon dioxide is transported via blank, and the most oxygen is transported via blank. We have red blood cells, hemoglobin, plasma, red blood cells, plasma, and hemoglobin. So, go ahead and pause the video, and check your text, check your notes, and get me an answer. 5, 4, 3, 2, 1. The correct answer is D. Most of the carbon dioxide is transported in the blood plasma in the form of a bicarbonate ion, and most of the oxygen gas is going to be transported bound to the hemoglobins within our red blood cells. Let's continue on with white blood cells. Our white blood cells also come from red bone marrow, just like the red blood cells and just like the platelets. All blood cells come from the red bone marrow. Our white blood cells are the only cell, the only mature cell of our blood that contains a nucleus. So if you're doing DNA fingerprinting of someone based on a blood sample, you're going to be pulling that DNA from their white blood cells. The production of white blood cells is going to be regulated by a hormone known as colony stimulating factor. This colony stimulating factor can be found in tissues as well as white blood cells can be found in the tissues of the body, actively patrolling and screening and fighting infections, and they can also be found in our bloodstream. White blood cells make up the immune system. They are the primary component of our second line of defense and our third line of defense. Particularly our adaptive immune system. Some of our white blood cells are capable of living for just a few short days, while others can live for months or years at a time, particularly if we're looking at the memory lymphocytes. Those can live in our bodies for years. So, here is a figure showing your white blood cells. Some white blood cells, the first three on top, have speckles in them. We have neutrophils, eosinophils, and basophils. And all of the phils, the PHILs, if they end with a phil, they have speckles. And those speckles are called granules. So we have the granular leukocytes, the white blood cells with speckles. And then we have the white blood cells without speckles, the agranular leukocytes. And our agranular leukocytes are going to be the lymphocytes and the monocytes. Generally speaking, our neutrophils are going to be well, I'll talk about this more in each slide. So if you want, you can zoom in and read this, but I'm going to talk about this in more detail as we progress through. So let's talk about our granular leukocytes. They contain those granules and lobed nuclei. So if you see funny shaped nuclei within a white blood cell, that's a big clue that you're looking at a granular leukocyte. Although probably you would be distracted by the fact that there's all these speckles all over the place. The neutrophils contain very light colored speckles, the eosinophils contain pink or red colored speckles, and the basophils contain dark purple speckles. Let's back up a slide here. So we have lighter colored speckles, the red colored speckles, and this slide is deceptive, actually. This should have the dark purple speckles, and this one should have the few light blue speckles. A granular leukocytes, though, are the leukocytes without the granules, and their nuclei are going to be, generally speaking, round in appearance. Our neutrophils are the most common leukocyte, the most common kind of white blood cell. The mnemonic is never let monkeys eat bananas. And that stands for neutrophils, lymphocytes, monocytes, eosinophils, basophils. And if you can remember, never let monkeys eat bananas, you can remember the most common kind of white blood cell to the least common kind of white blood cell. So neutrophils are the most common. That starts at the beginning of the mnemonic, never let monkeys eat bananas. And basophils, since that's at the end of our mnemonic, is the least common kind of white blood cell. Our neutrophils are the first line of defense. They are the kamikaze pilots, so to speak, in that they will sacrifice themselves to destroy or phagocytize any pathogens. Neutrophils are the primary component of pus, for those of you who have ever had the joy of having a pimple pop during your teenage years. Our eosinophils are much rarer than our neutrophils. They are only going to be more common than the basophils. Our eosinophils contain red granules and have a bilobed nucleate. The primary purpose of an eosinophil is to fight off a multicellular parasitic infection and, to a lesser degree, moderate or mediate allergic reactions. The main thing I want you to focus on is that eosinophils are red in color and help us to fight multicellular parasites. We also have basophils. Basophils are the least common white blood cell, and they are going to be primarily involved with mediating allergic responses. When you think of allergic reactions, I want you thinking of basophils. I want you to connect allergies to basophils. Our lymphocytes are the second most common white blood cell, and our lymphocytes are going to be involved with our active or adaptive or specific immunity. There's multiple words that are meaning the same thing. These are the white blood cells that allow for you to be exposed to a disease and develop immunity to the disease, so that the second time you're exposed to it, you don't have the signs and symptoms of the disease. These lymphocytes will further develop into B lymphocytes or T lymphocytes, and then those will subdevelop into more specific cell types that help us actively fight off specific diseases from our bodies. Our monocytes are the largest white blood cell. They are much larger than a erythrocyte or red blood cell. Our monocytes primarily are going to be located within the tissues of our body, and while they are in the tissues of our body, they will further differentiate into a large cell known as a macrophage, which literally means big for macrophage to eat. A macrophage is quite literally a big eater. These macrophages use phagocytosis to engulf the pathogens. So if you ever watched that 1950s classic, The Blob, you can think of the blob as a giant monocyte roaming around the town, swallowing cars and people and buildings. How do we get white blood cells from our bloodstream to the site of infection? We need to have those white blood cells exit the bloodstream. And they'll do that through a process called diapedesis, where they will squeeze their cell membrane and nucleus and cytoplasm out between the gaps of the blood capillaries into the extracellular matrix of the tissues. There are some disorders or diseases associated with white blood cells, just like there are with red blood cells. One is severe combined immunodeficiency disease. This is the disease that an individual can develop when there's where their stem cells that develop into their white blood cells don't have an enzyme that allow them to fight infection. So they still have white blood cells, but they're impotent white blood cells. They're white blood cells that can't actually destroy the pathogen in our body. So It's unfortunate because those individuals are immunocompromised and that they have a very, very difficult time fighting off infections with their defective white blood cells. We also have another disease known as leukemia. Leukemia is a cancer of the white blood cells in the blood, where there are too many white blood cells made in the blood. It's not that these are fully functional white blood cells. There is out of control growth of deformed white blood cells filling up the bloodstream. And these deformed white blood cells crowd out the functional white blood cells so that the patient has a compromised immune system. Another disease is infectious mononucleosis, also referred to as mono or kissing disease. And this disease can be caused by the Epstein or EBV, Epstein-Barr virus. This virus will specifically target our lymphocytes, so our B and T cells, and makes us have a lot of fatigue, we become very sore, we have swollen lymph nodes, and if anyone was ever lucky enough to have that disease, you know that usually the general remedy is resting a lot for several weeks. Well, you lose a couple weeks of your life. So, class, concept check. The most common kind of white blood cell, and the primary reason pus is white, is the neutrophil, lymphocyte, monocyte, eosinophil, and basophil. If you don't remember, that's okay. You can use the mnemonic, never let monkeys eat bananas. Pause the video and get me an answer. 5, 4, 3, 2, 1. The correct answer is A, neutrophil. The most common white blood cell is the neutrophil. And that is all we have for this lecture recording. If you have any questions about this course material, please feel free to stop by my office and give a holler, or you can shoot me an email or post them in the class discussion board. Happy studies!